Assalamualaikum and hi. So this is our second part of vector calculus. Okay. So now we want to know the del operator. So operator is represented by the symbol here. The symbol triangle, but you have bowl. Okay. Triangle terbalik ni. Okay. But you have bowl di sebelah kiri at the left side of the triangle here, and then we call del this as nabla, also as a nabla. But what is del and nabla? Del is an operator, okay, that dia adalah satu operator where we use to differentiate, okay, to differentiate a vector, okay, as a vector differential operator. So the nabla is also called as, or the nabla or the del operator is also as a function to differentiate a vector, or we call it as vector differential operator. Let's say if you have a function, okay, your function is only in one dimensional domain, so we just apply the symbol d, okay, just the standard form of d to differentiate the function. But if you have a vector, especially in the multi-dimensional domain, so in order to differentiate your function, you need to apply, or you need to use the symbol nabla or del. Okay, so the del or the nabla, in short, we can say that the nabla or del is an operator to differentiate a vector function, or it can also be said as a vector differential operator. So that is the introduction of del or nabla. So we proceed to know what the del operator or the nabla can do. The del operator can operate on a function. Okay, the del here, okay, del operator or the nabla can operate on a scalar or a vector function. When the del operator operates on scalar function, it will become a certain or a new equivalent function. When the del operator or the nabla operates on a vector function, it will become another new equivalent function. Alright, so the del operator, okay, can be written as here like this, okay, and this del is actually in the form of del x of component I, del y of component j, and del z of component k. So that is del operator, and it is also here. When a del operator operates on a scalar field, okay, they operate on scalar field, you will get a gradient. Okay, what is gradient? During our form 4 and during our matriculation level, we know that the gradient is represented by a slope of a function of a tangent line of the slope of a tangent line of a curve at a specific point. So that is a gradient. Okay, it also shows that the slope is actually the rate of change of a function. Okay, so inilah yang kita katakan berkaitan dengan the gradient. Okay, we want to know the slope of a function. Okay, and what is the slope? The slope represents the rate of change of the function. Okay, gradient of a scalar function of a scalar field. It is a vector field that points in the direction of the greatest rate of change of the scalar field. So this is the definition of the gradient. In order to get the gradient, you must have, or you must be given a scalar function. Okay, you must be given a scalar function. Then you have an operator, del operator. When the del operator, okay, del operator operates on the scalar field. Scalar bukan vector Scalar field. Scalar field means that you don't have the direction. Okay, the function does not contain any direction. So we call it as a scalar here. Okay, we name it as phi. Del operator operates on phi, where phi is a scalar function. So this is what we call it as gradient. Okay, gradient equals to grad of scalar function. We call it as phi. It can be f, it can be g, whatever symbol that you want to use, as long as it does not contain any direction, or it is not a vector field lah. Okay, so grad phi is equivalent to del operator operates on scalar field. This is equivalent to ini kan. This one is actually del x, del y, del z. Okay, since this is a scalar, ingat tak tadi awal-awal, okay, at the early of our discussion, when we have a scalar and we want to have the multiplication of a scalar, we can just bring the scalar into your process. So the same thing goes here. So you have to put phi. Okay, this one is just a scalar, so you masukkan sajalah dalam ni. Okay, you substitute the scalar inside your derivative here. So let's say your phi, your scalar function is given by x square yz cube plus xy square z square. So this is a scalar form. Okay, you don't have ij component, ij and k component. So this is a scalar. Okay, then if we want to find the gradient of phi is actually del phi. Del is del x, okay, comma del y and del z. Operates on your phi. What is your phi just now? X square yz cube plus xy square z square. So you just bring this one, your phi, inside your differentiation. Okay, partial derivative. So del x, differentiate your x square yz cube. Okay, comma del y, substitute your phi x square yz cube plus xy square z square. Alright, move skip. Comma, okay, you have del z and bring your phi x square yz cube, right, plus xy square z square, close. Alright, so this means that you want to differentiate x square yz cube, sini ada lagi lah, plus xy square z square. Okay, differentiate your phi with respect to x. Okay, remember when we apply the partial derivative, only x is your variable. Other than x, you must treat it as a constant. Differentiate constant will give you will give you 0. So when you differentiate according to the component I, j and k, you will get this solution. This is for component I, this is for component j, and this is for component k. Okay, that is for grad phi. Okay, but the question is find grad phi. Okay, find the gradient phi at point P1, 1, 3, 2. 1, 3, 2 means that this is for x, this is for y, this is for z. So you just substitute x, y, z into, x equals to 1, y equals to 3, and z equals to 2 into your solution. Therefore, you will get your solution specific values here. Values of I, here j and k. So substitute lah. This x equals to 1, y is 3, z equals to 2. So 2 cube multiplied by the rest of the numbers here so that you have specific value. So that is the solution. Alright, so this is the solution lah after you substitute the value of P equals to 132. Okay, so what I can conclude here is the del operator, okay, del operator when it operates on a scalar function, we call it as gradient. Okay, we call it as a gradient. Then what I can say more is when a del operator operates on a scalar function, you will get gradient where the gradient is in vector form, no longer scalar. So as you can see here, the solution in the form of vector. Okay, asalnya tadi, okay, initially you have scalar. Del operator operates on scalar, you will have gradient where the results of the gradient will give you in the form of vector. Understand the first one? Okay, next we move to the second operation on del operator where the del operator operates on vector.